Okay, looks like more and more people joined, which is a good thing. So yeah, I will also have textbook itself opened, and we're still busy chapter 1. We're looking at system calls. Yeah, all right. Are there any questions on what we've covered so far before we jump onto system calls? Okay, none. There seem to be no questions. So, okay. Okay, so I'll just quickly maybe speak about virtual memory again. Um, Virtual memory actually gives the ability, and it's discussed in details in chapter 3. We will, as we study memory management, discuss it in more details. It actually gives the ability to run programs larger than the machine's physical memory by rapidly moving pieces back and forth between RAM and disk. So uh, for someone to understand the concept of virtual memory, they need to understand that there is physical memory, the actual one we can refer to on a computer and say, okay, we've got so much space in terms of gigabytes or megabytes. Virtual memory becomes a technique, and as you know, ROM or permanent data is stored normally under ROM, which in this case will be represented by the disk part. RAM is just a temporary memory storage through which data transits as it's being manipulated, but eventually it has to be stored under, eventually it ends up being stored on the disk, meaning under ROM. So if you can find the mechanism to rapidly move part of the data back and forth between RAM and disk, rapidly meaning quite fast, then you will have created some form of extra memory, because you would have extended the memory on disk through RAM. So you will be you will have found a way to use RAM somehow as part of your disk, because the physical memory is what you have on the disk, but in this case RAM will also play the role of storing some of the data that would have been stored in the disk. This explains why when it comes to virtual memory, whenever power goes off, you also lose the data on that virtual memory. So it's only available as you run. Okay. Yeah, so we will look at that in more details in chapter 3, as I mentioned. But now system calls. Okay. What is system call? We need to understand that, but we also need to understand how it's applied in a Unix context specifically. Okay, we've seen that operating systems have two main functions. As we said, and I expect everybody to know that the management of computer resources, we have kept on saying it over and over. So that's one of the major functions of the operating system. The second one will be it provides abstraction to user programs. How does it provide abstraction to user programs? Remember, when you're sitting at the much higher layer, sorry, when you're sitting at a much higher layer, so I'm talking, remember the layer of in a computer organization, all the way from memory to application through the user interface programs. The operating system, as you noticed, was creating a transitional layer between the application on the top side as well as memory. Is that okay? So it is the one that is used to it's used as a platform or a transitional platform to talk to the hardware, but to serve who? To serve the user programs, Word, Excel, calculator, any form of application you can think of, the Home Affairs, such as Home Affairs registration application, for example, etc. So the operating system definitely plays an abstraction to user programs. In a sense, why abstraction? Because at the user program level, you are accessing, for example, the Bluetooth modem, but you don't necessarily have to know the hardware details or the firmware details of that Bluetooth modem at that layer, because through the operating system you can just enable Bluetooth in your application, for example, or you can shut it down, or you can ask it to search for other Bluetooth, I mean active Bluetooth devices in the area, or through your program you could pair to a found device, etc. So the operating system has created that abstraction between the Bluetooth modem that you don't, in this case, talk to directly, and yourself sitting at user program development point of view. Okay. For most part, the interaction between user programs and operating system deals with the former, meaning the managing of computer resources is actually the main or the core function of an operating system. Okay. So creating, writing, reading, deleting files as an example. So that's all management of resources. Without an operating system, we don't necessarily have the ability as a user to do all of those tasks. But it's thanks to it that we are able to do that. Okay. The resource management part is largely transparent to the user and done automatically. Transparent to the user goes back to what I explained, is that the computer in the background is handling the yes, DS, you wanted to say? Your microphone is open. Okay. So I was saying the management of computer resources is transparent because I as a user, when I'm trying to, let's say, save a new file that I've created in Word, I just say save, just click save. As for how Windows finds, first of all, space where to save that file, or how it's able to check and find out that I can't save anymore because I'm out of the memory space I have left is smaller than the size of the file. Windows works all of that in the background. That's why we say it's transparent. Okay, the operating system is transparent to the user when it comes to its purpose or its function of managing computer resources. Okay. So the interface between user programs and operating system is primarily about dealing with the abstractions. Exactly. So most of times we, at the user point of view, through a program or through using end user computing, meaning using the computer, typing on the keyboard or on the mouse, we actually need the interface on the operating system so that we can how can I put it? It can serve as a way to deal with the abstraction. Otherwise, and that's what one of the major differences between operating systems, for example, is that, for example, Windows has got more visuals or more interfaces, graphical user interfaces, which then allows the user to become, it makes it easier to use. When it comes to Linux, as we'll notice as we embark on using Linux, is that we'll deal mostly with we'll deal mostly with the system through the command line, and that it will be done in form of scripts as well as how do you call it? Script as well as command lines basically. Okay. To really understand what operating systems do, we must examine the interface closely. Okay, so like an interface like the one in front of me right now, the application opened here is Foxit Reader to read a PDF file. Okay, if I say file, and then I say save as, all of this is happening in the background because once I say save as, the Windows is already checking, do I have enough space to allow this file to be saved in that memory space, etc. So by just looking at the graphical user interface, you are able to sort of get a glimpse or an idea of how the operating system is managing the resources in the background. Okay. So what is system call, and why did we have to go through? You'll understand now why we had to go through all of that introduction, which is more of a revision. It's because when the system calls, okay, in general, in plural, sorry, or in general, the system calls available in the interface vary from one operating system to another. Okay, we yet to define what system calls means, but they vary from operating system to operating system. In other terms, in Windows, you might have an option to check the memory size of a USB, for example, through the interface. You right click on it, you say properties, you get the value. But you may not necessarily have that privilege in Linux, for example, or in Mac OS. So the calls, and I think I have to now define the system call here, is that system calls has to do with the call that someone makes at the user interface program level for resources through the operating system. So a reading from memory call, a writing to memory call, a printing call. So all the calls that you make at application layer to interact with the resources, meaning memory, etc., through the operating system form what we call system calls. Okay, and we are saying that they are available in the interface, but that varies from operating system to operating system. Okay, this is why we are forced to make a choice between, okay, vague generalities, meaning operating systems have system calls for reading files. That's vague generalities. Why is it a vague generality? Because every operating system will normally have a system call for reading, memory in general. But since memory in most operating systems is organized in terms of files, then that's what we're speaking about, reading files. Okay. In general, we'll be reading data, but in all operating systems, most memory is organized in terms of files. Okay, so that's more of a vague generality, meaning you need, as a user, whether you are a program interface developer or just a normal end user computer and user computing expert, meaning someone just using a computer, you still need most of times to read files. Okay, meaning let's take when I'm using a PDF reader like Foxit in this case, for example. When you go and say file open and you click on a file, what happens is that you read the content of that file from memory. And that's a general type of system call. The second thing we must, because we're making choice between vague generalities as well as some specific system, okay, some specific system system calls. So depending on an operating system, from operating system to operating system, we have some system calls or functions that are specific to that operating system. In the category, for example, of line, okay, Unix, under which falls Linux. In the category of the different Linux operating systems, we have, for example, one called Kali Linux, yeah, which is more specialized for security, for example, as a typical example. So it is normal that this operating system being specialized for security will have system calls for encryption of files, for example. You might have a system call for AES encryption, for example. So encryption is one of the key special system calls you expect to get out of this operating system. Is that okay? Because it's a security operating system. Just as an example, okay? So the choice is often to be made between those two. So as you embark on a task in your day-to-day IT expert's job, when it comes to deciding which operating system will serve your interest better, you often have to choose between vague generalities if your job just entails some general aspect, or specific system calls. Depending on whether you're developing for security on Linux, you might need Kali Linux, for example. But if you're just developing on C++ on Linux, you may use any Linux platform such as Ubuntu, etc. Okay. Here, for example, in the specific case of Unix, it said that Unix has a read system call with 3 parameters: one specifying the file, one to tell the data where the data are to be put, meaning You say, I want to read this file. Then you say, once I've read it, I want to put the content of it in this other file, or which could be on the screen, etc. So the destination, basically. And at the end of the day, how many bytes of that file I want to read. Is that okay? And we'll do all of this in practice as we go towards practicals. Okay, this Wednesday. We have chosen the next approach. The later approach, meaning the one of specific system calls. Okay, it's more work that way, true, but it gives more insight in what operating system really do. And here I'm slowly landing towards why in this subject, as we learn operating system, we will go more towards Unix rather than, for example, Windows, etc. Because through Windows has got enough graphical user interfaces that sort of shadows your ability to understand how the system really works. But in Linux, because most of things are done from command window point of view, you get a chance to basically better understand the operating system functionality. Okay, that's the idea. Okay, so that's a motivation for why we chose, as we teach you about operating system, to rather focus on Unix types, and specifically in this subject we'll learn Linux. Okay, but within the category of Unix operating systems, because it's a family of operating systems, we have a couple of very popular other operating system other than Linux. These include POSIX, we've got System 5, BSD, Minix 3, etc. And of course Linux, which is the one we will study. Okay, and we have other modern operating systems that are Unix based. They've got systems. What is the particularity of the modern operating systems that are Unix based? The modern ones is that they have the particularity that the system calls they have are capable to perform the same functions as a normal Unix, but this is despite the fact that details may differ. I gave an example of Kali Linux, for example, which when you do a memory read on could return not only the content of the file, for example, but it could also tell you whether the file is protected against read or not. So it brings in that extra content, which is the security aspect of that operation or of that system call. Okay, since the actual okay, the reason why I revert back to the textbook quickly is just to give you a sense of more details, because you get much more details in the textbook rather than in the slides. But yeah, I'll jump back to the slides now. Since the actual mechanics of issuing a system call are highly machine dependent, meaning a system call as it gets executed through an operating system on demand of a user interface program, of course, it still has to go all the way down to the physical hardware to execute. Okay, that's why we say it's highly machine dependent. So it depends on the machine. Whenever we speak about machine level, we are actually referring to low level, meaning hardware level. Okay, and this is the reason why system calls are mostly written in assembly language. If there's anyone who knows about assembly, raise your hand. I just want to get a sense of how many of you through a previous module have learned about assembly, or heard at least. You've definitely, what programming language did you study so far? Can anyone say?
Java.
Oh, Java. Okay. Java is quite a high level type of code. So if you were to go in the categories of programming languages, you get what we call high level um, languages, and that is where your Java sits, for example. Okay, and you do get low level languages, and of course middle level, like your C language is kind of middle level. And at the low level where you speak directly to the hardware exists what we call assembly language. Okay, language. It might become handy, but But if it does, then we'll learn about it. I think why am I saying it might? Because as we uh, manipulate lower levels of memories, we might go back to assembly, and I'll have to show you. It's quite a straightforward language because it goes from a set of instructions that exist, and then you combine them to use it. Okay. All right. That's important. Okay. Um, Okay, so I'll use the book again here. Uh, so we're talking about system call, of course, and we're saying it often uses it. I mean, it's often highly machine dependent, meaning it quite happens at the lower levels. The mechanics of it, in terms of the process of execution of it, happens at lower levels. Hence, the justification for the use of assembly code when it comes to most system calls definitions. So if you are defining a system call, you tend to go towards the use of assembly code because you are sitting at machine level. A procedure library is provided to make it possible to make system calls from C programs and often other languages. So because assembly language is not often very user friendly because it's really low level, as I mentioned. Just to give you an idea, when you're writing an if statement, for example, on a byte of data, meaning yeah, you know bytes because you use the byte data type in Java. So I can stick to that example. When you're trying to do an if statement, let's say on a byte of data, if you are using Java or C++ or any other higher languages, it's as good as if this variable is equal or higher than, and then you carry on. When it comes to assembly, for example, you need at least 8 statements because you the only because you are sitting at hardware very close to hardware level. You do the test bit by bit. For example, to check if 2 bytes are equal, you'll check if all their 8 bits are identical, and you see how tedious it can get. It's because of that. But at the same time, we have the requirement that because system call is at lower level, it must be in assembly. But to make up the gap between them was invented some procedures, and to be specific, procedure libraries, whose purpose is actually to serve as translators of some sort. So you write your code, a system call function or a system call instruction in C++ or in Java, then it will be given to that procedure library that converts it or assembles it, as we often say. Remember, when you compile, what happens is that the compiler assembles your code, meaning it converts it to the equivalent assembly code. And it's that generated assembly code that gets given to the actual resources, hardware resources on the computer system level in order to execute. But you at the user level, you're sitting with higher level programming, and you have a translator in between that we call a procedure library. Okay. It is useful to keep the following in mind. Yeah, it's very important because a lot of people, when they program in Java, they think they are not necessarily aware that there is actually a procedure library that converts through compilation the code from C, C++, Java, and so on into assembly language because that the language that at machine level is understood. Okay. Any single CPU computer can execute only one instruction at a time. Yes, so there is no multiprocessing in a single CPU computer. Um, Remember what we said is that you'd have to have multiple cores to achieve multi-threading, and even multiple CPUs to achieve to achieve multiprocessing itself. So the fact that if you're working on a single CPU, you execute one instruction at a time, and that results in type of programs that we often call sequential because they execute one line by line. Okay. If a process is running a user program in the user mode and needs a system service, such as reading data from a file, for example, it has to execute a trap instruction to transfer control to the operating system. Okay, what does it mean, a trap instruction? So let's put this in perspective. So someone is running a user program. Okay, so you're developing, let's say, your application somewhere, and you just got like a button, for example, and that button is written on top print. What that means is that if someone clicks on that, maybe it will take a file in a specific location and print it, for example. So, so what that means is that the user program in this case is the graphical user program. I mean, interface program, like any GUI of some sort, Java based or C# or any other language. Okay, if you were to run it in user mode, running a program in user mode, what does it mean? It means you are trying to do some of the functions that the user of the computer system would have done by means of clicking or using the keypad, etc. Is that okay? But you trying to do that at your within your program. For this includes things such as for example, printing, as I said, when you are a user using an operating system, you normally take a couple of steps, which makes it a process, because process means couple of steps in a certain order as you want to print. So if you are trying to do that now through your application, all of these steps still need to be taken. It's just that it's kind of automated, and uh, the fact of having that process that would have been carried out by a user of the program automated is what we call the trap instruction. And what it does is it transfers control to the operating system. So it's actually passing on to different commands to the operating system to execute as if the same way the user would have done manually. Okay, that's what we call a trap instruction. The operating system then figures out what the calling process want by inspecting the parameters. So as the trap instruction is given to the operating system in this automated scenario, it will figure out what should be the system calls in their respective order for the process to execute. Okay, and it does this thanks to the parameters that are provided with the trap instruction. Okay, very important. The operating system then figures, as I've said that, then it carries out the system call and returns control to the instruction following the system call. So it also comes up with a return, which in a case of printing would be successful, or maybe there's an error or something like that. Okay. In a sense, making a system call is like making a special kind of procedure call. Okay. Only system calls enter the kernel and procedure calls do not. So we should make a difference between system calls and procedure calls. Although system calls look like procedure calls when they are automated, the difference is that system calls affect directly the kernel part of the computer system, while procedures do not get to that level. Is that okay? Procedures are more sitting at a much higher level, meaning they don't interact with the kernel. They're sitting at the user interface level. Procedure, as you know very well, procedure which leads to functions. Okay. So the next layer above procedures is functions, but both procedures and functions sit at application user interface level, while system calls, on the other hand, actually go all the way down to the hardware. Hence, they go through the kernel. To make the system call mechanism clear, let us take a quick look at the read system call. So the fact of reading a file. As mentioned above, it is the three parameters. A read file system call will normally have, you must be able to specify, beside the command, you must be able to specify the file you are reading, the destination after reading, and how much quantity of that file you want to read. Those are the three parameters that you must have in a read system call, for example. Okay, now I've just responded them. Like nearly all system calls, it is invoked from C programs by calling a library procedure, as I explained earlier, which will actually assemble it, as we know. So a library procedure with the same name as the call. It's often a read function that we call. I'll give you a typical example. Scanf in C. For those with that, C in Java, system IO get line, for example, or read line. So what they're trying to say is that here is that you often find the keyword read or get, specifically read, in the library procedure that get called at a higher level language programming. So in C, for example, you would have a read or a printf for putting data. That is a write type of system call. Printf falls under the category of write system call because you're writing data to a certain memory. But here, since the examples read, most of times the procedure, the library procedure will normally have a name that includes the keyword read. That's what we're trying to say. Okay. Typical example here in the C program will be read fd buffer. Fd will therefore be the file we want to read. Buffer will be where we want to save the data we will have read, and byte will be how many bytes we want to read from that file, because sometimes you don't want to read the entire file but part of it. Okay. The system call and library procedure return the number of bytes actually read in count. So as a return, or as part of what get returned from the read instruction, is the number of bytes that eventually got read by calling the read function. Okay, this value is normally the same as n byte. This is in the case where you're trying to read the entire file. Okay, it will play around with this in Linux as we do a reading of a file through the console, for example. Unlike in Windows, where to read a file, we'll just double click on it, for example, and it will open. Just going back to the reason why we chose Linux over Windows as we learn operating system. Okay. Okay. But this value of count is not necessarily equal to n byte. Sometimes n byte is smaller than that because you may not want to read the entire file. If the system call cannot be carried out owing to an invalid parameter, meaning out of memory or any other reason, okay, then the count, which was supposed to read the data from the file and get incremented as data is being read byte by byte, is normally set to -1 whenever there's an error. There's a way to reset it. And this does not matter whether the error happens while you had started already reading and something get disconnected or anything like that. It will just reset the count. And if you were writing to a memory space, let's say another file called buffer, and you are not done writing, then you might end up with an invalid file. Okay. Okay. The error number, because errors vary a lot, they are also given IDs, which we call error number. And this error number is normally put in a global variable. And the global variable, when it comes to operating system, for keeping or saving all errors, is what we call ERRNO. I'm sure you've seen this, and it just stands for error number. ERR is for error, NO is for number. Programs should always check the result of a system call to see if an error occurred. So if you are writing your application in Java, for example, at the user interface program level, if there's an error, you must always cater for handling it. That's what we call exception or error handling in your application, so that the user does not get confused by staying in the dark, not knowing what happened to the files. So they need to be given a certain error number, which is normally defined by the operating system to correspond to a set specific type of error. Okay, programs should always check the result of the system call, to see if the error occurred. System calls are performed in series of steps. So a system call is actually on its own sort of a procedure, as we said, with the differences we highlighted. That's why it's performed in series of steps. So it's step by step. and sometimes system calls could be repeated, in which case everything will normally restart from scratch, from step one, carrying on. To make this concept clearer, let's examine the read call discussed above. In preparation for calling the read library procedure, which actually makes the read system at the end of the day, the calling program, could be a program in Java or anything like that, will first push the parameters onto the stack. And that's clearly illustrated in figure 1.17, which is this. So the parameters that are needed will normally be pushed onto the stack. Okay, and which parameters are we pushing on the stack? We are pushing on the stack a couple of things, including the bytes, number of bytes we want to actually read, for example. Okay, you want that to be part of the stack already or pushed onto the stack. In languages such as C and C++ compilers, push the parameters onto the stack is in reverse order. So most of these programs are little Indian, meaning they push the data onto the stack in reverse order, starting then with the least significant bit going towards the most significant bit. Okay, a typical example would be printf in C, for example, okay, which has to do with printing data on a screen. In a console application, the format string when used with printf, meaning %s, appear on top of the stack. So when it comes to ordering things, if there's any type of string, it will normally appear on top of the stack. Okay. Yeah. And that's because we're sitting at IO level, input output. Printf is an IO function or procedure. Okay, because it helps. Although we don't necessarily, and that justifies why we don't necessarily have access to how it's defined, because it actually is abstract. It provides some abstraction through the operating system to the user. So a user does not have to know how printf calls read inside and which memory at the end of the day get read. In modern operating systems, all of that is handled automatically. Okay, that's very important. I hope you guys can still hear me. It sounds more like a one-man show. Let me see. There seemed to be a message in the group. No, it was deleted after. No problem. Okay, so the first and the third parameters are called by the value, but the second parameter is passed by reference in a printf. Most of the time, this applies to Java as well. You often have you could have a system print line dot out where you pass string mixed with values, for example. But if it's a value, then you'll have to do a specifier for it, let's say %s, so that, and then you'll put the variable name of the value so that the compiler, as it assembles, it knows where to find it. Okay. Addressing data by referencing uses the ampersand sign, as you know very well. When you studied pointers, clearly you touched on that. Okay, the first and the third parameters are called by value, but the second parameter is passed by reference, meaning that the address of the buffer is passed. So what we put is the address of where the buffer is. So that's why we're saying that it is passed by reference. Okay, so we don't use the actual buffer's variable name, but we use its address. Okay, then comes the actual call to the library procedure, which is in step 4. And the instruction is the normal procedure call instruction used to call all other procedures. Okay. The library procedure possibly written in assembly language most of times. So printf is what you have at the C++ point of view. But the actual implementation of printf is mostly it's probable to be written in assembly because it's talking directly to the memory space or to hardware. Okay. So that's about the different steps that get involved when it comes to a system call and what it is. The trap instruction, as we mentioned, is very useful. But there is a last step in the system call, that is step 5, which has to do with the fact that the library procedure, possibly written in assembly, typically puts the system call number in a place where the operating system expects it, such as a register. So throughout execution, the system calls are given IDs or numbers, and this number of this system call is normally placed in some location, memory location, of course, in this case, such as a register, where the operating system is supposed to be expecting to get it. Yeah. And once it does get it, it examines the trap instruction to switch. So it makes sense of the trap instruction, which is an automated form of system calls, with a couple of steps to be taken, more like a script. Okay, so that need to be assessed. Okay, so after assessing that, then the trap instruction is actually executed, and as it gets executed, okay, by the operating system, of course, then if we take an example where the trap instruction is executed to switch from user mode to kernel mode and start execution at a fixed address within the kernel, then we're talking about a specific set of instruction, as we said, called trap instruction, which, as we know, is normally supposed to operate through the kernel. But in this case, it will go from kernel mode to using a fixed address within the kernel. Okay. The trap instruction is actually fairly similar to the procedure call instruction, in the sense that the instruction following it is taken from a distant location, and the return address is saved on the stack for later use. So when you get a return value out of the program, that's normally return value normally is stored on the stack. Okay, that's very important. Okay, so there are other steps leading to system call, and all of that over and over. A typical, because it's not all, a typical system call when it comes to an operating system would have around 11 steps to be executed by the procedure in order for it to satisfactorily. Are there any questions? Are there any questions, guys, before we move back to the slides?
No, sir.
Yes, go ahead. You are saying?
I was saying no questions, sir.
This part is mostly theoretical, but you get used to it as we carry on. And yes, you need to know it. There's no way we can teach about the operating system and just jump into using Linux. We need to know the underlying principles. So when it comes to system calls, the actual routine, because we say for every system call is an associated procedure. The actual routine, which is the procedure, is normally found in a table. And this will be a lookup table, if we can call it like that. And the system calls do work. I mean, the routine executing the system call, which is found in a table, what it does is it does the work involved in the call, so one by one. That's normal. And after the routine is executed, it returns to the user program some information which could be valuable for the next system call or for the functioning of the application itself. Typical examples with the read we pass as parameter how many bytes we want to read, but the routine executes and it gives us back how many bytes we actually did read, which is not necessarily equal to what we wanted to read, because a problem could happen and we could end up with less bytes before we finish the reading. Okay, so that is quite important. So we've looked at the Unix read system call and its three major parameters as we discussed, as well as its return. We looked at its actual diagram, but I'll explain this a bit more now. Is that as you've noticed, SP is involved. The stack is involved in a read call on Unix. When you see SP, it means it's a stack pointer, which defines where we are in the execution. So in the stack pointer it's the one that will be keeping the step at which we are as we execute the procedure that is involved, that defines the system call. So in the stack, we'll go from 1, 2, up to 11, depending on which step in the procedure we are at. Okay, that is very important. When it comes to system calls, we will start by learning the fact that they start with process management. So we'll start by looking at the process management of a system call. We'll look a bit how they are used in a shell. You know what a shell is, we defined it last time. And then we'll learn how to write our own shell scripts, meaning sort of set of system calls. Remember what we said, every system call is made up of a procedure. In a shell, you write a script, and every script is made up of system calls. Okay, and the shell executes the script. Okay. Then at the end, we'll do a brief summary of calls, and we will apply them to things such as file management and some other useful calls. That is mostly in what we'll be doing, even in the other coming chapters. So let's look at system calls for process management. Okay, these will be special type of system calls that are specifically meant for helping with the management of the process. Okay, by the operating system. So typical ones include what we call fork, and the purpose of this system call when it comes to process management is to create a child process identical to the parent. And that the name of it makes sense because it's like that. You know, that's how a fork will look like. So for so if it's like branching out, but this is the parent, and these will be the children. So when you say fork at an operating system, you're actually creating a duplicate of the parent call. Of the parent process, a duplicate of the parent process, not call. The call is fork, but it duplicates the process, creating a child which is identical to it. The next type of call we have at process management level is wait PID, okay, which has to do with waiting for a child to terminate. I'll give a typical example of where that is very important. For example, in the printing application, user application, let's look at printing as a user application. Normally, you would want, when you are busy with printing, you would want a process to terminate, a process of checking if, let's say, you've got a link through the network to the printer to finish before you actually send the actual image or the actual file you want to print as an image to the printer. You don't want to send the image before you've checked if you have a link to the printer. So a typical child process is birthed. It's child to the major process, which is check connection. Why is it a child? Because there could be multiple people trying to print at the same time, for example. So there is a generic parent process that has to do with network link checking. So everybody, as they are trying to print from their own station, for example, will generate a child of that process. But the point here, wait PID will ensure that the checking of the connection link is finished before the actual file is sent to the printer. Okay. Another very important process management call is execve, which has to do with replacing a process's core image. Okay, the process's core image. So every process has got what we call a core image. Now you've learned a couple of things that you are involved in the process. Is that you have an ID for every process. You also have what you call a core image of a process. And when you do execve, you're actually trying to replace the core image of a process. So it's like modifying the process. Okay. And you pass to it the name, of course. By the way, in PID, it returns the PID, which is the process identification. In wait PID, it returns PID, the process identification. You passing the couple of other parameters. The second one, because of the percent, is said to be passed by reference. Is that okay? It's said to be passed by reference. How you detect that is that you've got the percent, which says we giving the address of that memory location instead of the actual variable. Okay. And other options, because most of times we probably have to specify that if the child does not never terminate, what next? So the process management need to know, yes, we're waiting for it to terminate, but if the wait PID happens not to terminate, what will be the system call happens not to terminate? What shall we do as a next step? Okay, that's the idea. So we will use wait PID in C as we program some process management. And as I mentioned, there's a procedure therefore that will convert the C code we'll be writing into assembly. Okay. All right. So that's a special type of system called in Linux, in Unix in general, wait ID, as we mentioned. In terms of what we pass on to it, we have the child processes ID, which is the PID. Okay. Then we have the start lock, which has to do with how far we are in the execution of the process that we are waiting to terminate, as well as the options. And among the options, we could have a lot of options, part of which include things such as all, which would mean that wait for any child. So it's like waiting for any type of child process, meaning it's sort of overshadowing the PID that you will have passed. And that could be useful to say, before I do anything in this process, let's say you having your Word is freezing, your PDF is freezing, or multiple applications are frozen. You might have that might kick in as a process management called wait PID, which would ensure that with all under option, to ensure that all of those processes must first terminate before we carry on. Obviously, very important at process management point of view is the exit instruction, finally, which the purpose of is to terminate the process execution and return status. And remember, exit can happen naturally when the process is really at the end, or it could be prematurely executed in case the user, at the user interface point of view, wants so, through a program or by an actual user clicking somewhere. Okay, so those are the 4 core system calls that you find when it comes to process management in a Unix operating system. memory layout, we spoke about this already, but we're coming back on it because it's important to understand how memory is organized in a computer system for someone to understand how the interaction of this memory happens. So at a very higher level, we have what we call the stack. The stack is the immediate type of memory layer, as I explained. We've seen this a similar diagram before. Is the direct memory that the operating system can access quickly. Then we've got the gap, and then we reach what we call data. There's a gap between stack and data because data does not immediately get sent onto stack unless needed there. Okay, and when we speak about data, we are sitting at a layer where you start speaking, let's say, about file. Is that okay? File will be a typical example of a data. Below the file is the actual text, for example, the actual characters, the actual ASCII coded type of information. That's what we call the text, and that is really sitting at the bottom layer. Okay. A typical shell, because we said we write a couple of shells, we're going to write them, some of them in assembly, some of them in C. This is a typical shell program or a script or program to be executed by the shell. This one is written in C, right? And as you can see, it's using a couple of process management functions. It's saying while true, which means always, all the time. So this should happen all the time. Okay, that's what while true means. And while true, it says type prompt, and type prompt simply means display prompt on the screen. So it's a way to say to prompt the user to input something. Then the user obviously will have to type in a command. Then the next instruction is read command, which reads the command together with its parameters. Then we check if fork, right? If fork different from 0, which means if we are able to create a duplicate of the process, meaning we are returning a PID different from 0. Because when we return 0, it means we were unable to create a child process. Because when you create a child process, it gets given a new ID. So because PID is the return of fork, then when it's different from 0, that means we successfully did fork of the child process, meaning birth a child process. Okay. Now, if that is successful, then we will, at the parent level, code level, we will say wait PID, and what that will check is that it will make sure that we wait for the process to execute before we do anything else. Okay, wait for the child to exit, because we were successful, that means we're starting with the execution of the child. So we need to make sure the child finishes its execution before we carry on. That's where the wait PID is useful here. But in case we didn't manage to get a child process, which is when fork is actually equal to 0, meaning which can happen in 2 ways. Either the child has finished executing, or we just don't have resources to ensure that the child executes. And that way we're in the else part, and in there we will execute the command that the child process is all about. Okay, and there we call the process management system called exec VE. Okay, very important. That's a typical type of shell application, the type of which we'll be writing in this subject. And it's broken down again step by step. Whatever I just explained is what is explained in the next couple of slides with examples, of course. And in any programming language, including C and Java that you know of, there's normally what we call a main program or a main process. And in a main process or procedure rather, or function, sometimes we call it main method when in Java, or main function when you're in C. It's normally receives a couple of key argument. Okay, first of all, what is it? The main procedure or method or function is the procedure from which the operating system start the execution. So everything is executed from there. It normally has a couple of arguments which include the number of items in the command line. Okay, how many items do we have in the command line to be executed? Argument count, so that is argc. Argument argv is argument values. Those are the actual items on the command line. Okay, but they are organized in form of an array. So if there are 3 of them, the arrays will go from 0 to 2. And finally, the last argument you normally pass to the main procedure is envp, which actually points to the environment. Okay, to the environment, which has to do with so an array of name, which is equal to the value of info like terminal type. What that means is that the environment here has to do with where on the computer system this type of command is pointing towards. Let's say it's pointing towards a file, all right? So then the environment will be carrying out the path to that file as a typical example. Okay, system calls for file management, because there are some special calls for file management besides the one we just learned now, which are for process management. When it comes for file management, because remember an operating system, and you must keep that in mind, one of its major functions is to manage resources. Some of those resources include processes. That's what we learned about process management. Then other resources include files, of course, especially memory resources. It has to do with files. And we call file management because memory is mostly organized in files in most computer systems. And some of these functions you've already used, right? A lot, actually, in Java. I'm sure you did some file manipulation, and you learned about the opening system call, the close system call, to which you pass the file pointer or file ID, the read, the write, the lseek, which has to do with moving the file pointer. So for example, sometimes you want to read a file but not from the beginning, so you might move the pointer inside the file, let's say to 10 with an offset, meaning offset representing the number of bytes of 10 bytes. Then if it's text, it will skip the first 10 characters, for example. Okay, then you also have what we call stat. You mostly used in your, I'm sure by now you mostly use open, close, read, write. Those you definitely used. For those who went a bit far, they would have used lseek as well as stat. Stat gets the file status information, meaning is it a read only, is it write file, etc. The name of the file is part of things you specify as you call stat. And buffer is you pass some memory space where this information about the file will be stored at the end of the day. Okay. Of course, when it comes to file management, it's very important to know about file modes. Okay. And the system will normally keep track of this, because when you opening a file, you might be opening it for reading, or you might be opening it for writing. And the system needs to know what you are opening it for, and it will keep track of that. So that you know about file modes. And yeah, the mode when it comes to files is often read, write, or both. Okay, or append, by the way, which would mean I'm opening it, I'm having an offset, and I'm writing from where I left. Okay, so stat is a typical system call when it comes to file mode management in any language, basically. But on a higher layer, we went from the process to file. On a much higher layer, we've got what we call system calls for directory and file management. So not just the files themselves and their content, but the files and their organization. And as we know very well, in most operating systems, files are organized or grouped into directories. We've got mkdir, which in short stands for make directory, which means create a new directory. We've got rmdir, which has to do with removing an empty directory. You've got link, which creates a new entry with a second name, name2, for example, pointing to name1. So such way that from that moment on, the two files or the two directories are linked. So you can refer by name2 after execution of link. You can refer by name2 to a file called name1. Okay. Unlinking is also important to undo the link. Mounting, very special. Mounting a file system, it's very commonly used. You mount a file system, and this is in this case it's a file system rather than an actual file. And this can happen on various memories, for example, CD, USB, etc. And you could also unmount it. For example, for someone to be able to read a USB, they must be on a given operating system. They must first mount it onto the local disk so that we can pull data from the USB onto general memory of the computer and be able to read it. And once you're done using it, you unmount it. Okay. The linking process, an example of the linking process is provided here. For example, which has to do with linking a couple of files in different locations. Okay, in Unix, each file is identified by an I number, which we call ID number basically. So every file you have in a Unix managed, meaning Unix operating system on a computer system, will normally have what we call a I number, which is like the ID of the file. The I number indexes into inode table. So there will also be therefore a table of nodes, and the I number will serve as a way to index or to point towards the within the table within the inode table to where that specific file resides. To create a link between two files, what happens is that you end up creating a new directory entry, meaning a new ID of some sort, with the same I number. Okay, so but a different name. So what makes the link is the I number. Although two files could have different names, they are linked. If they are linked, they definitely have to have the same I number. That's the point I'm trying to make there. Okay, the mount system call is explained here, and I sort of spoke about it when I spoke about the CD, memory sticks, etc. So I've explained this already. Then the third category, the fourth category besides process management calls, system calls, besides file management system calls, besides directory and file management system calls, is the category that we classify as other system calls. And in there, you get things such as change directory, which is very important because you might need to move from one directory to another as you manipulate files, and we'll learn a lot. We'll use this a lot when we do Linux, or changing the mode. And this is very important whenever you're trying to change the security of a file, maybe from read only to write, to be able to read, to becoming a read write, so that you can, for example, edit its content. Okay. Of course, we also have killing of a process, and that's more at process level. You might want to terminate the process by killing it. For example, on Windows, the kill system call is called when you go to system task and say end task. What the process that call there is called kill, is the kill process actually. Then very important in some or in a lot or a number of applications, you might need to time or to get a sense of how long you've been executing a process for, and for various reasons. And we call a system call that we call time. You've seen, I'm sure you've used time in many places, including Excel or any other programming language. There's always a time constant, a time function, sorry, system call. And what it returns is it returns the number of seconds since the 1st of January 1970, and that is what we call the Unix time. The Unix time, sometimes referred to as epoch. I mean, this date is epoch. Sorry, epoch is that date. Epoch. Okay, is that date, 1st of January 1970. So the number of seconds from that date to current to now, basically on the computer system, is the Unix value. Okay, Unix value is the number of seconds there, and we'll do some manipulation with that as we embark onto practicals. So here is a list of some of the equivalent processes to the Unix processes we just learned when it comes to Windows. Okay, so fork on Unix is equivalent to create process on Windows 32, for example. And here, when we say Win32, we refer to a Windows operating system with a word length of 32, because there's also Win64. So just to give the equivalence, I'm sure you know about read file. So when you're doing C++, for example, on Windows, what happens is that you read file is the command you execute, or if you are executing it, writing a batch script, as we call them in Windows, you would normally use read file in your script. But if you're on Linux, you use read only. So that there are some equivalence between the two systems, between the two operating systems when it comes to their system calls. Next is the operating system structures. The structure of an operating system. And when it comes to an operating system, we can have different types based on the structure, or meaning how things are organized. First, we've got what we call monolithic systems. In a monolithic operating system, a main program, as we saw, a main call, a main system call, meaning a main procedure, is the one that invokes the requested service procedure. So everything is requested from the main program. Monolithic, as you know, has to do with a stone or something like that. So everything is centered around one thing, which is the main program. That is in the monolithic systems. A set of service procedures that carry out the system calls. There's a set of service procedures that will carry out the system calls. Okay, but they are all called from the main program. A set of utility procedures that help the service procedures. So we've got main program, service procedures, and utility procedures in a monolithic system type of operating system. Okay, there is an example. So we have normally a main function. Let's see. No, there is a main function. There are a couple of other procedures. Let's stick to procedure. So there's a main function or program. Okay. And from there are called the different procedures. And there are two categories. We've got service procedures as well as utility procedures. So between the two, inter-region as well as leave region, they are both of the same type. These two, inter-region and leave region, would you classify them as service procedures or utility procedures? Anyone? Anyone want to try? And why? The inter-region and the leave region. Or maybe I'll remind you, a service procedure carries out the system calls. So when you're entering a region, and here we're referring to a memory region, this is a service, you agree? Because a utility procedure is just there to help the service procedure. So this will be things such as, let's say, a procedure that calls the mounting before you read a file, because from a USB, because you need to mount a USB or a CD before you read any file from it. So the one that mounts will be a typical utility procedure, for example. Okay. All right. When we do practicals, things will make much more sense. But beside the monolithic operating systems, we also have what we call layered systems. And layered systems, it's not all in one block. its couple of layers on the operating system. So, and this is mostly popular. Okay, it's mostly popular, and we have up to 6 layers identified by IDs from 0 to 5. You've got a layer of the operator, so that's the highest layer where you, as I'm moving the mouse like this, I'm sitting at that layer. The user program will be something like PowerPoint. The input-output management part of the operating system will have to do with how, when I've been maybe editing this file, when I'm about to save it, how is it saved, in which part of memory and where. The output, for example, has to do with how this page ends up on the screen like this. The input has to do with the fact that when I type on the keyboard, some data might end up on this page. So if I type the A, the part that's handling the fact that A ends up on there is part of this input management layer. The operator process communication. This is more at the API level, meaning the translation between my commands and the actual processes that leads to their execution. Okay, and memory and RAM management, that's at lower level, where the actual memory storage is managed. Okay, in terms of will data fit, will data not fit, for example. In the case of saving this file on a USB, my USB is almost full. The part of the operating system that checks that is sitting at layer 1. And at the bottom layer, we've got processor allocation and multi-programming. So this has to do with the CPU part and how it allocates its processing resources, which are basically the ALU, the arithmetic part and the logic part within the ALU. And multi-programming part has to do with how would, in the case of multi-threading or multi-processing, how would multiple cores of the same CPU coordinate the execution of a certain processing task. And in the case of a multiprocessor, how would multiple processors, CPUs on the same computer system do that or manage the execution of the multiple of a process with multiple execution paths. Yeah. Okay. We're almost through. Let me see if we'll be able to do all of that. Okay. I think we'll speak about microkernels all the way to 67 tomorrow before we embark on chapter 2. And after tomorrow's class, I'll give you an assignment, and on Wednesday we'll start with the practice. Or actually, we'll just study a piece of chapter 2 tomorrow. We do the practicals on Wednesday, then only I give you an assignment. Then it will be you'll be able to already do the assignment using Linux. So what I'll give you today is also, what I want you to do is to be able to install Ubuntu Linux. We'll use that. Okay, I don't want you to clean your computer, but I want you to create a virtual machine. I hope on your personal computers you've got enough space for that. Because as you noticed, they say we won't go back to face-to-face unless needed. But for that, I'll need to give you permits, of which I don't mind giving in case people don't have computers. But those who have their personal computers and they're quite good enough, I'll just tell them what to install, and they can still use their computers. Yeah, we'll see. But if we need to be in the lab, we need a permit. We'll get a permit and go to the lab, because not everybody has necessarily a computer. So I would like you to basically create a virtual machine and load Ubuntu on it. Ubuntu, the latest version, like Ubuntu Linux. Okay, latest. Let me just check what will be the latest version. Ubuntu desktop, of course. 20. So you have to let me write. It's like a homework before tomorrow. Let me type it onto your group. Okay, yeah. If there are no other questions, we finish for today. I'll see you tomorrow. I'm just typing the homework in here that we must make sure you've done by tomorrow. You can use VirtualBox. Download and install a virtual machine application called VirtualBox to download Ubuntu Linux, that specific version, Linux desktop, and load it on the virtual machine. So when you create the virtual machine, okay, you create a virtual machine that you should call by your student number. Maybe too long actually. Just call it OSY2160. Okay, so that is the homework before tomorrow. Happy? Any questions?